All right, calculus. So you'll be watching this Thursday night. So I kind of lost track of the date, so you can fill in the date for me. I have the topic of continuity for you, and we'll look at half of a board at a time, and I will adjust it when we go off of the first half. If you would please call the topic of discussion continuity. Continuity involves limits, so I'm going to teach it now where we're kind of fresh talking about limits. So the most understanding will be gained. So what is a continuous function? Basically, if you can draw the function without lifting your pen or your pencil, without lifting it, or another way we could say it is there's no hops, skips, or jumps in the drawing of the function, then you do have a continuous function. So is that rigorous enough of a definition for us? No, no, no. So let's add a little rigor to our understanding of continuous. I've drawn for you up here some functions, and I'm going to talk about the continuity of each. This one is non-continuous, and it has a jump, a hole right here, so we could call that one a skip. We'll call that one a skip. And so I can't draw it without picking up my chalk. It is non-continuous at this point. If you would observe that, you will see that the function is not defined at C. So leaving that one alone, let's go down to B. On this one, we see that the function is defined at C. Right there it has a dot, if it shows up, but it still cannot be drawn without picking up your chalk or pencil, so it has a jump. So I don't know, these words are just common terms, they're not mathematical for now. So this one is an example of non-continuous. It comes down as following a pattern, but then it has a hole and it jumps down and has a value off of that pattern. Non-continuous. This one at point C, we can see there is a definite jump. The function is going up and then it starts down and goes like that. It is a function, but it is not continuous. And graph D at C can be drawn without lifting our chalk or pencil. At C, you'll notice, is the point where you might have the most question, but it is continuous. Even though it has a sharp turn, it is continuous. Now, one of these is called having a removable continuity, and that is the one where the continuity a function can be written very quickly to remove the hop, skip, or jump. So the one that has a removable continuity is this one. I'm sorry, a removable discontinuity. So we observe as we come from the left and the right at C, the limit is the same. It's this value, whatever this is, we'll call it L. So it does have a limit at that spot. We've been well taught about that, but it is not continuous. So it's called a removable discontinuity because I can easily remove it with this function. I can say this function, I can redefine it as the function where x does not equal c, but when x does equal c, we're going to call it L, the limit. So see how quickly, without even knowing the name of the function, I can redefine a function quickly that has no discontinuity. So I remove the discontinuity quickly, because all that means is where x doesn't equal c, the function looks like this. But at x equals c, it's going to equal the limit. So it will actually color that back in. So this function is quickly obtained from this one. This one is continuous. This one is not. All right, so that's how I remove the hole, basically. All right, let's go back to one with a hole. And again, this is called removable discontinuity. This one is not as easily removed. I'd have to know more about this one, and this one is not, and this one's already continuous. So there's only one that's called removable. Just a definition you might meet along the way. All right, let's look at the other side of the board. If I go too fast, just go ahead and stop the video, and we will get all the information down while you pause, and then turn it back on. Definition of continuity. Here's where we add the rigor to our idea of continuity. A function is continuous at C, so we're talking about only at one point is it continuous, and if the function evaluated at C is defined, if the limit as x approaches C of the function exists, and the limit as x approaches C of f of x equals f of C. If you notice, these are somewhat related to graph A, B, and C. So number one says the function is defined. Over here on graph A, the function was not defined at all at x equals C. So therefore, it's obviously not continuous. Here where we're defining what is continuous, we're going to say that the function is defined at the point of interest. All right, C. So 2, the limit as x approaches C of a function exists. Then we talked earlier, and I tucked this in, just a reminder, this is not new. The limit exists if you come from the right and the left and they are equal to one another. So let's look at which graph over here is affected by that requirement. The limit as x approaches C of f of x exists. Well, this one, it does exist from the left and the right, but this one, it does exist from the left or the right. It's over here. So this second part of the requirement must be aiming at this kind. Because notice as we come in from the left, we get a value up here for the limit. As we come in from the right, we get a value down here for the limit. So the two limits are not equal, so we say the limit does not exist. And that is a way we can find if it's continuous as well. So if it doesn't exist, we know we have discontinuity. If it does exist, we go on to the next requirement. The limit as x approaches C of the function is the function evaluated at C. So let's look at graph B and see how that falls short of that requirement. Here we have the limit from the left and the right are equal, but when we go and put C into the function, we do not get this value right here, we get this one. So it's badly behaving function. So think that through and see if that makes sense to you, that these three requirements, if they are met, we will always have a continuous function. We will not have one of those badly behaving functions over there. Let's go on. A function is continuous on an open interval. An open interval means we are not including the endpoint. So anything up to A on the right, left, and up down to B on the right, we are not including the endpoints. A function is continuous on an open interval. We call it AB with parentheses. If it is continuous at every point in the interval. So that's what we're talking about continuity at a point so far. Now we have branched out to continuity of an interval. So an open interval is easier to cover first because all it means is that every point on the interval the function meets the continuity requirements. Let's look at the next requirement. We're going to close the interval now, and the interval will look like this. The function is continuous on a closed interval. We put brackets around it, and now we've added a problem. We've added endpoints. So let me draw a little picture. Sorry, I have to keep going back and forth. Let me draw a little picture here. When we have a function, and say this is point A, and this is point B, and the function is going to have endpoints. We're okay without the endpoints with this definition, that every point between A and B, x equals A and x equals B, every point in between is continuous, then we say the open interval is continuous. But once we add these points here, the endpoints included, notice how they fail on some of our requirements. Can you look at the 3 requirements and tell me the endpoints, which ones fail? F of c is defined. How about this one? The limit as x approaches c of f of x exists, which again I reminded you is the limit has to equal the same from the left and the right. So unfortunately that's the one that this fails. If we cut this function off here at a and b, the limit exists as we come in from the right, it's L, but when we come in from the left, there's no function above it to connect to. So therefore, we do not have a function that exists because it comes in from the right but not the left. So yet this is going to happen. We're going to have functions that start abruptly at certain points and end abruptly at certain points. And we are willing to call them continuous. So we have to add a special case when we have a closed interval a to b. So the way we handle that is a function is continuous on the closed interval AB if it is continuous on the open interval, so that's all the points in between A and B, and now we have to look at the endpoint. So the endpoint A, written on the left, we're only requiring one-sided limit, and that's the limit from this side, from the right, because the function doesn't exist on the other side. So therefore, we are only requiring the limit to exist on one side for f of x, and it will equal f of a, so there's not going to be a badly behaving function there. And what do you think the rest is? I'm going to say I left a cognitive hole. See if you can fill it in. See if you can see where I'm coming from and where I'm going. If I dealt with this endpoint, now what am I going to say about the other? The limit as x approaches b from which direction? So notice we don't have anything on the right, so we're on the b, we're going to be coming in from the left. That's the little negative side. The limit as x approaches b from the left is going to be equal to the limit of f of x as x approaches b from the left is going to be f of b. So when we plug that value in, the function, it does not jump around or anything, it's actually on the curve. So as we get closer and closer to b from the left, the function has this as its limit, f of b. Alright, so let me switch the camera to another board, so we'll have part 2 in just a minute.